Hello everyone. From now on, I will use English as my main language to do the teaching. You may be confused why I will use English, and for one thing is that I will practice my oral speaking skills, and for the other, I want all of you, that means my audiences, to get accustomed to the speaking of English and get accustomed to the terms of physics in English. So from today, I will use English as my main language, and the videos will be posted on the two platforms, that Bilibili and YouTube, and you may just to see through it if you want to see it. Okay, as you can see from the title, that is quantum information and computation, and that's very important. So, from your mind, you may just an idea pop out. What is quantum, and what is quantum information? Right? This is a very important and very critical question. What is quantum information? Why does it matter? You may be confused because if you are keeping pace with the modern technologies, and you may find that the quantum computers are still under experiment. They have not been put into the market for people to use. So what is the quantum information? Even if it has not been created, even if it has not just provided the opportunities for job landing, like the coding, programming, etc. So why does quantum information matter? Now I want to first tell you is that the quantum information and the quantum computer, they are based on the basic principles of quantum mechanics. So in this term and in this subject, the quantum mechanics, I want to say that is the foundation. Okay, it is the foundation. So I will not hesitate to tell you that the quantum information and computation still holds its value, and even if it may be confusing to you at first glance, I want to tell you that after listening to my courses, and you will feel very bright and very insightful to this subject. Okay, that is the interface of the courses. So the section 1 is that, right? Because when we talk about the quantum information, I want to first introduce to you a role, that is a phantom. You might be accused that, might be curious about why I name myself the Professor Fountain in the YouTube channel. That means that phantom is very important. Sometimes you may have heard that the Einstein has called the phantom, it has wave particle duality, right? You may have heard of that. That is because the Einstein said that. However, I want to say that photon is photon. It is just a basic particle. It is just a basic, like the existing, the being in our physical world. So I want just to call it photon rather than the wave particle duality. So you may be confused. What is the difference between the photon and the wave? Because we all know if you just look up and look at the light, you may be just can know that our light is essentially the electromagnetic wave, right? In our real life, the wave is actually the electromagnetic wave, or you can say magnetic field. So it is essentially this. And the photon, Einstein has said that is a wave particle duality. So what is the difference? Now I want to introduce to you an experiment to explain this. That is the MZ interferometer. And in Chinese, it means MZ 干涉仪. Okay, so I want to know that what is the difference between the two subjects that is like the photon and the classic electromagnetic field? What is the difference when they operate in the MZ interferometer? Okay, interferometer. Okay. So we first want to know the structure of the interferometer. And you may be confused that what is the essential aspects of interference. And in the interference, I want to first introduce to you some components in the optical physics. That is the first, the BS. The BS means the beam splitter. And please allow me to describe it as this component. Okay, this is the BS. And the second one is just the very common optic in our experiments, that is the mirror. And the mirror, you will always see that here is some like the lines, shielded lines. And if a light, for example, the electric field goes and it will just be reflected back. Okay, this is for the mirror. It's very interesting and very simple. What about for the BS? You can see that it's called the beam splitter, right? So when light goes in, it will split into two, and one is transmit, and the other one is reflected, right? This one, I will show you about this. This one just reflected, and this one will transmit. So what is the difference? What does it change in the process? Okay, for simplification, and we only consider the 50-50. Okay, 50-50 beam splitter. That means that if here I told you the formula for the incident beam is E0 to the power I omega t. Okay, I do not consider because many of you will just pump out that, wow, the wave, it should be expressed like this, E omega t minus kz, and if the kz is the propagation direction. Okay, for simplification, I do not consider the propagation of the wind, of the wave, but only consider, wow, it just stays there. Okay, I want to consider the basic principle, but not the transmission properties of that. So I will just simplify it as this, just as I show in the picture. So if we consider it as a 50-50, what does it mean? It means that here the amplitude will become square root and 1 over square root 2, and here is either. Right, because its amplitude will just be 1/2. Why it is square root 2, and here is 1 over square root 2. Why not is 1 over 2? That means 50-50 is to the power, and for the amplitude, or for the amplitude of electric field, it should be just give it, add it as square root. So here, I will say I omega t plus phi r. The subscript capital R means reflect. Okay, and here for the transmission part, I will say that it is 1 over square root 2 and E0 E to the power is omega t plus phi t, and t obviously it means translation or transmission. Okay, so that is obvious. You have observed that I have added the phases into the terms, and the phases in Chinese it means 相位. Okay, so I introduced the two phases, that is phi r and phi t. I want you to tell you that in our case, that is 50-50, that is split the power evenly, and the phi r and phi t, their difference is certain. Okay, phi r minus phi t always equal to pi over 2. I want to emphasize that the phi r minus phi t equals to pi to 2 is only making sense in our case, that is 50 to 50 the power and the 50 to 50 the beam splitter. So that means that when you change the distribution of the reflective and the transmissive, just the beam, it will always change. There is no more pi over 2. So in the most common cases, we only consider the 50 to 50 the beam splitter. That is very common in our experiment. So you can bear this formula, this correlation between the phi r and phi t in mind. That is very useful. I want to tell you that. So some of you may also ask, wow, the beam splitter, will it cost the energy? Will it consume the energy? And will it waste energy? And of course, for different materials and for different just the workshop or the workcraft and the working process, the production process for making the beam splitter, and the different beam splitter will consume the different degree of energy. So here, for the ideal part, we do not consider any consumption of energy. The energy will be conserved. Okay, so that is for the details of the beam splitter. And the second is the mirror, right? And the third, I want to introduce another one, that is the phase shifter. Okay, the phase shifter, please allow me to express it as this. What is the function of the phase shifter? That is very obvious because from the name you know that the phase shifter is to just shift the phase. That means when light, for example, when light here, it's initially the phase is omega t, and when it goes through the phi, the phase will always go to omega t plus phi. That is the phase shift. Okay, here are the main three components. Okay, three components in the MZ interferometer. Here I will introduce to you what will the wave behave in the MZ interferometer. Okay, because I have introduced the three components, the three optics in our experiment, so it may be very understandable that I will introduce the structure of the MZ interferometer. The structure, it seems like this. Okay, here is beam splitter, as you can see, and here is the mirror that is just entirely reflective. Okay, and here is another the beam splitter, and here I want to show that for the wave part, please remember that now I consider the wave, not the fountain. For the wave part, and we just express the wave as a function as the expression we have introduced before, that is E equals to 0, 0 and E I omega t. Okay? Okay, that is it. So when it goes through the beam splitter, as I can show you, part of it will just reflect back and part of it will transmit through the PBS, the BS, okay, the beam splitter, not the PBS. Okay, I have just flipped my mouse. Oh, that's okay. Just the BS, okay, the beam splitter, just I considered, just I discussed in the just the former sentences. Okay, so here when it reflected, what will just the amplitude? What will the expression for the wave? So here it is 1 over square root 2, and here is E0, and okay, and here is E I omega t plus phi r, right? That is very simple. And what is for this one? That is go through the bottom mirror. Here it is. 1 over square root 2 E0 E I 2I omega t plus phi t, right? That means the transmit. And when it hits the mirror, it does nothing, just to redirect the beam. Okay, here the direction is here, and it goes into the second beam splitter. Here it is. Also, does not change anything. So I just keep it as this. And here it also does not change anything. So it will also be just like this. Okay, it goes into the second beam splitter. So as you may have observed, if I just denote it as up prime, okay, here is up and here is down, that is for the initial state, and here is up prime and down prime is for the final state, and up prime, what is the components of it? Or you can see that it is composed of. Obviously, it composed of two parts, and one part is through this. I will show you. Is this and reflect, right? And another part is this, and that is goes here and transmit. So here are two parts. The two parts I will show you, that is 1 over square root 2 E0 E I omega t plus phi r, always also plus phi r. And you may have neglected one thing, that is, you should also times 1 over square root 2. That's because it reflects again, so its amplitude will be also times another 1 over square root 2. So here it should plus the green line. The green line should also be E0 EI omega t plus phi t, always plus phi t, and also times here, right? This is for the up prime. And also for the down prime, you can just express it, but we only consider one thing for just a simplification. We only consider the upside. So here it is. It should be omega t plus phi r UK. That is 2 times phi r. That is 2 phi r. Okay. And E0 E I omega t plus 2 phi t. And you may be confused that I have introduced to you the phase shifter, but it does not exist in our structure of the MZ interferometer. That's because I have a lot of drawing here. So I want to join now. Okay, I will add a phi here. That means I add a phase shifter here. So something will change in our just the formula in the expression for the up prime for the outcome of the upper beam. What will change? Right? This formula must change to a new one. And what is the new one? Okay, this new one should be this. And nothing changed except the phase. So why it is called a phase shifter? That's because it only changes the phase. Oh, here, phi r, and also you should plus it. You should plus 1 phi. Okay, and here for the bottom beam, it does not change anything. So here it is always this. Omega t plus 2 phi t. Okay, so this one is very important. That is the basic rule of our MZ interferometer for the wave, that is for the electromagnetic field, that is this one. So you must keep it inside, keep it in mind, and bear it. Okay, it is very important. So some of you might have also learned that interference, that means interferometry. In physics, we also call it this. That is interferometry. Okay. In the interferometry, it considers, and it is just the focus on the intensity of the up. For example, here is a detector. Okay, here is a detector. The detector will just calculate the intensity that goes into the upper beam. Okay, so here it is. This is the detector. Okay, just as I have said, the E up prime is this. So what is I up prime? The I up prime should be E up prime times E up prime, the conjugate, right? This denotes the conjugate. So here you should do just like the mathematical just calculation here. So that is seems very difficult, but I want to see that it is actually not difficult at all because you have know one thing, that is phi r minus phi t equals to half over 2. Right? This is very important. This is a condition of presumption for our calculation. So here I want to show that first there must be this. That is for the first term here. And for the second term here is also this. And please do not forget that we have something more important, that is 1 over 2 and what? Right? 1 over 2. And the sum interference terms. And how can you calculate it? Right? How can you calculate it? And in the following, just for the simplification, I want to leave it to you as a homework, or you can just calculate it. This is very simple. And I want to show you how to calculate it. That means the 1 E0 EI omega t plus 2 phi r plus phi and plus 1 half E0 EI omega t plus 2 phi t and 8 terms times here E0 E minus I omega t plus 2 phi r plus phi and 1 half E0 E minus I omega t plus 2 phi t. And I want to tell you that the EI phi just equals to the cosine phi plus I sin phi. So here for the power, it always be not the imaginary numbers, but the real number. So here I want to take it as the real number. Okay, this is for the real. So the concentration, the outcome is very beautiful. I want to say it is the most beautiful thing that I have seen in the physical world. That is the 1 over 2 or 1 half and 1 plus cosine phi. Okay. I do not remember whether it is plus or minus. Please let me check it first. Okay, sorry, I made a mistake. Okay. Without calculation, I even cannot remember the result here. That means here the result is, you may check it yourself, that is 1 minus cosine phi. Okay. So here that means that you can tune the value of phi. For example, if the phi equals to 0, what does it mean? It does mean I up prime will be 0. So it means that all the light or all the electromagnetic beam will go down, will go to the bottom part. And what about phi equals to pi? If phi equals to pi, the cosine pi equals to minus 1, and also here it is I up prime will be E0 squared. That means that all the light, all the intensity will just go upside, with no intensity goes to the downside. That is the I down prime equals to 0. That is very important and very interesting and basic physics in the optical physics. That is very important and very beautiful. So you may have seen that this is for the wave. Okay, I think this section, that is 1.1, we may just tell you about the wave. About the fountain, I will tell you in the next section because of time limitation. But in the end of the course, I want to tell you some basic, that the simplification method I want to use in the next courses, that is the vectorization. Or you can see that I will use the matrix to simplify it. Okay, I will use the matrix to simplify it. Matrix to simplify. That means the B, if I denote it to the beam splitter, it can be expressed in a matrix, right? You have always known that the beam splitter, it will just add some of the phase, because here when it reflects back, it will add a phase, the phi r, and when it just transmits, it will add a phase phi t here. So that is very important. I want to tell you something about that. So for example, if a beam goes in, right? For example, if I say here the E0 I omega t and here's 0. So this vect just denotes a beam or electromagnetic wave just goes from the upper side. So when it goes a beam splitter, it will just become two parts, right? It will just be reflected back and it will just transmit through the beam splitter. So here, for the upper side, what will it change? It will change it like this. E I delta or no delta. Oh, you can see that delta, right? Also phi, okay, no delta, okay. Phi what? For the upper, it's just reflect back, so phi r. And here I do not know because it times 0, so I do not know. And for the down level, what will it be? Right? What will it be? So here I do not know. Or here do I know? You please think. You please think. Do I know the things? Right? What will it change? I want to tell you that there is a not right here for the expression for the matrix of the beam splitter. So here it must be this. Okay, it must be this. You must forgot that there is an amplitude, the shift that is the 1 over square root 2, right? Oh, here it must be what? It must be 1, that is unitary here. And the other side I want to show you, that is, here is E, right? E what? And here is also E. What is the power? That is what's the 2. Here it must be E I phi, right? Just you can just do the calculations here, and I want to show you. It must be, here is 2 times 2 matrix, and here is 2 times 1 matrix. So here is also what just like the 2 times 1 matrix. Okay, and here we know the result, that is the E0, and for the reflected part is omega t plus phi r, and for the transmission part it is I omega t plus phi t, and also please be clear that here is 1 over root 2 for the amplitude shift. So here I want to show you that it is, this must be the phi t and it must be the phi r. Okay, that is very important thing here. And Oh, sorry for I was confused about the expression of the beam splitter because I have no paper here. Just talk without any thinking. So, what about the using the mirror is just to redirect the direction of the beam, so that does not matter. So, what about the phase shifter? That is, we denote it as P. Right? The phase shifter. What does the phase shifter do? For example, if here also E0 I omega t, that is from the upper arm of the system. And when it goes around wave shifter, it will be changed into I, that is the phase will change, the omega t will also classify, here is bracket and here is 0. So you should add also a 2 times 2 matrix here. What does it be expressed? It can be expressed as this, right? Okay, is that simple? Is that simple? Yeah, actually it is very simple. So it is one thing is for the beam splitter and the other is for just the phase shifter. And the matrix expression should just be like this. Okay, should just be like this. That's because it also always shifts the growth rate. For the upper part, it just keep the same. So here is 1. Okay, now today in this section that please denote as to the end, we denote it as section 1.1. This is about how the electromagnetic field will behave in the MZ interferometer. That is very important, very paramount for understanding the quantum information, and it will show in later courses. And then in the next section, I will introduce to you the photon, how photon behaves in our MZ interferometer. That is also very interesting, and it must be somewhat different from what we have today, because the quantum information, the quantum mechanics is just like a ministry, and not so many people know them, right? So that is very tricky and very interesting. And see you next time. Bye.